Welcome to this comprehensive presentation on resin transfer molding, or RTM, a closed mold composite manufacturing process. In this advanced technique, dry fiber reinforcement is placed inside a rigid matched metal mold, and liquid resin is injected under pressure to fully impregnate the fibers. The result is a high-performance composite part with excellent surface finish on both sides, superior dimensional accuracy, and outstanding mechanical strength. As we can see in this detailed 3D view, the process involves an upper moving mold, a lower fixed mold, a dry fiber preform, and precisely controlled resin and vacuum systems. This process is widely used in automotive, aerospace, and high-performance industries. The foundation of every high-performance RTM part is the dry fiber preform. This engineered skeleton defines the part's geometry, thickness, fiber volume fraction, and final mechanical performance. On the right, you can see a typical layup sequence using multiple layers of woven fabrics, biaxial materials, unidirectional fibers, and core materials. The microscopic view reveals the complex fiber architecture with bundles, crossover points, and tiny flow channels. Proper preform design ensures controlled resin flow and minimizes defects. Consistent and optimized preform architecture leads to predictable flow and superior composite parts. Once the dry preform is placed in the mold, the next critical step is mold closure and compaction. As the upper mold closes with significant force, it compresses the preform, reducing its thickness and increasing the fiber volume fraction. This compaction removes excess air, minimizes voids, and creates optimal permeability for resin flow. The visuals clearly show the before and after comparison: thickness reduction, higher fiber packing, and significant void elimination. Achieving the right compaction pressure and speed is essential for uniform quality and excellent surface finish. Before resin injection, vacuum is applied to remove trapped air, moisture, and volatiles from the mold cavity. This step is crucial for achieving void-free composites. In the animation, you can see blue airflow arrows as air is systematically drawn out through vacuum ports and vents. The system includes a vacuum pump, trap, and manifold. Maintaining vacuum levels between -0.8 to -0.95 bar ensures complete air evacuation. A good vacuum today ensures a perfect part tomorrow. Proper sealing and leak detection are vital for success. With the mold closed and vacuum applied, resin injection begins. High-pressure resin is driven into the mold through the injection port, overcoming flow resistance and advancing through the fiber preform. Watch as the yellow-green resin flows, displacing air ahead of the flow front. The time-lapse visuals show how the resin progressively saturates the preform from 0% to 100%. Controlled injection pressure, flow rate, and resin viscosity are key to achieving uniform distribution and complete impregnation without dry spots or race tracking. Resin flow front dynamics is one of the most critical phases in RTM. The flow front must advance uniformly through complex geometries. This colorful simulation shows pressure distribution, saturation levels, and velocity vectors. You can observe how the flow progresses over time and identify potential issues like race tracking, air entrapment, or hesitation zones. Stable and uniform flow front advancement is essential for complete impregnation, minimal voids, and high-quality composite parts. At the microscopic level, successful RTM depends on excellent fiber wetting. Resin must completely spread over and penetrate between individual fibers to create a strong bond. The detailed visuals show the step-by-step wetting process. Resin approaches, makes contact, displaces air, and fully wets the fiber surface. Good wetting, indicated by low contact angle, results in strong interfacial bonding and high mechanical performance. Poor wetting leads to voids and weak interfaces. This microscopic interaction ultimately determines the part's strength and durability. Resin viscosity is the most important factor controlling flow behavior. As shown in this beautiful visualization, temperature dramatically affects viscosity. Higher temperatures reduce viscosity, making the resin flow more easily through the preform. The graph clearly displays the optimal viscosity window for perfect impregnation. Too thick, and the resin won't flow properly. Too thin, and it may cause leaks or dry spots. Precise temperature control of both the resin and the mold is critical for achieving consistent, high-quality results. Once resin and hardener are mixed and injected, the chemical reaction begins. Molecules start to connect, forming new bonds and initiating cross-linking. This dramatic molecular visualization shows the activation energy and the beginning of the transformation from liquid to solid. Temperature, mix ratio, and chemistry all play vital roles. Proper reaction initiation controls gel time, cure rate, and final properties. Getting the chemistry right at the start is essential for producing reliable, high-performance composite parts. After injection, the resin undergoes gelation and cure progression, transforming from a liquid into a rigid solid. The beautiful color gradient in the mold shows this transformation clearly. At the gel point, the resin loses its ability to flow as an infinite molecular network forms. As curing continues, cross-link density increases, delivering maximum mechanical properties. Precise control of temperature and time during this phase is crucial for achieving the desired strength, stiffness, and thermal performance. Demolding and post-cure complete the RTM process. Post-curing at controlled temperature enhances mechanical strength and thermal stability. Careful demolding prevents damage, and final inspection ensures the part is ready for service. Quality is built into every part through robust processes, not just final inspection. This slide highlights common defects, such as voids, dry spots, and delamination, along with prevention strategies. Advanced non-destructive testing methods like ultrasonic, X-ray, and thermography help ensure internal quality. Real-time monitoring of temperature, pressure, and flow front, combined with statistical process control, guarantees consistent excellence. Prevention is always better than detection. Every composite part must prove its performance through rigorous testing and validation. This includes pressure cycling, thermal cycling, burst testing, vibration, and environmental exposure. The validation pyramid shows how testing progresses from material coupons to full system validation. Real test data and simulation correlation confirm that the part meets all design requirements. Through comprehensive testing, we don't just hope the part works, we prove it. Finally, scaling from prototype to full production requires robust processes, capable people, reliable equipment, and a strong culture of continuous improvement. The roadmap, KPIs, and PDCA cycle shown here guide this journey. Excellence at scale comes from standardized work, empowered teams, and relentless focus on quality. Every day, we strive to build it right, make it better, and deliver exceptional composite parts that exceed customer expectations.